Now another concept with respect to the equivalent conductance. We have an equivalent conductance, and equivalent conductance is the product of specific conductance and the volume. Now obviously the doubt or a question arises that upon increasing the volume the equivalent conductance increases, correct? Upon increasing the volume this increases. How long it will increases? If it is 10 ml, 100 ml, 1000 ml or 10,000 ml, at 10,000 ml still it increases. Now we need a clarity how long the equivalent conductance increases upon increasing the volume, upon increasing the dilution. As the increase in the dilution, so how long the equivalent conductance actually increases? There should be a limit. Now the increase in the equivalent conductance reaches to a maximum value. It reaches to a maximum value at a particular dilution as the maximum dilution. Okay, when it reaches to a maximum dilution, the equivalent conductance stops upon increasing. It actually stops increasing. The equivalent conductance reaches to a maximum value in a particular dilutions. That dilutions we call it as a infinite dilution. So further increase in the dilution doesn't alter the value of delta EQ, will be constant, does not change. When it reaches to a maximum dilutions, the equivalent conductance reaches to a maximum value. So upon further increase in the dilutions does not alter the equivalent conductance. That is known as the equivalent conductance at infinite dilutions. We call it as equivalent conductance at infinite dilution. So the maximum value of the equivalent conductance of an electrolyte is obtained at higher dilutions. The maximum value, we will get a maximum value of an equivalent conductance of an electrolyte at higher dilutions. At higher dilution, we call it as lambda equivalent conductance at infinite dilutions. Simply it is denoted as lambda infinity. We call it as lambda infinity. So lambda infinity is nothing but the equivalent conductance at infinite dilutions. So infinite dilutions, what we mean that the solution is so dilute that any further dilution does not produce any change in the equivalent conductance of the solutions. If you increase, so it reaches to a maximum value when it reaches to an infinite dilutions. Upon further increase in the dilution does not alter or change equivalent conductance. Now in order to get the clarity of this picture, what we will do is we will plot a graph, the variation of the equivalent conductance with the dilutions, where the equivalent conductance of a different dilution is actually plotted against the C. So we take this graph. Now this is the equivalent conductance at different dilutions. Different dilutions is actually plotted against the square root of C, that is the concentration of the solutions, in moles per liter. This is in moles per liter. Now so we have two electrolytes. One is strong electrolyte, another is weak electrolyte. Strong electrolyte actually dissociates completely, Weak electrolyte dissociates partially. Strong electrolyte reaches to a maximum delta EQ, maximum value at higher concentration, that is lower dilution, reaches to a maximum value. But weak electrolyte reaches to a maximum value, maximum equivalent conductance at lower concentration, higher dilution. So because as the dilutions increases, the degree of dissociation keep on increasing the weak electrolyte. It actually increases, and as it reaches to infinite dilutions, it reaches to a maximum value. That is in the case of acetic acid. In the case of acetic acid, it reaches like, you will get a graph like this. So this is the acetic acid. Now with respect to KCl, we will get like this. So this is with respect to strong electrolyte KCl. So this reaches to a maximum value at higher concentration. So this is, you can see here, it reaches to as the concentration is decreasing, as the dilution is actually increasing. You can see there is a huge increase in the delta EQ, that is equivalent conductance, the sharp hike in the as it reaches to an infinite dilutions. So for acetic acid, the lambda EQ 392. 392 is actually equivalent conductance at infinite dilutions. Lambda infinity for acetic acid is 390. Now in all the expressions, what we have in the expression is actually the specific conductance, the G into L by A conductance. So this is observed conductance, and this ratio L by A is the ratio that depends upon the length of the container or length of the electrodes, which are separated by 1 centimeter each other, and area of cross sections will be 1 centimeter square. And this ratio we call it as a cell it's constant. We call it as cell constant. Denoted by X. So we can get K G into X, where X is a cell constant, depends upon L by A, where X is cell constant. So the cell constant depends upon the length of a conductor and area of cross section of the conductor. Determination of a cell constant. So cell constant is related to the specific conductance G into X. So where G is a observed conductance, this is specific conductance. Now if you take in order to calculate, we know that G is a, so where K is a specific conductance, where G is a observed conductance. So we can take a solutions of a known solutions whose specific conductance is already known. Now if say for example 0.1 normal KCl has a specific conductance of 002765 Simon meter inverse. So this is a specific conductance of a 0.1 normal KCl. Now in order to calculate observed conductance, just take a 50 ml of 0.1 normal KCl solutions dip in the conductivity cell and observe the conductance G. G can be known. So by knowing G and by knowing this specific conductance, it's possible to calculate the conductivity cell constant, that is K by G. So once we know the cell constant, then it is easy to determine the equivalent conductance of an electrolyte. And let's try to illustrate the methods to determine or measure the equivalent conductance. Measurement of equivalent conductance or determination of equivalent conductance. Now the first of all, determinations of equivalent conductance. Now the formula for equivalent conductance is actually Eq kappa into 1000 by C. So we know C, what is C is a concentration of the solutions, and the kappa is a specific conductance. It is a specific conductance. So in order to calculate the equivalent conductance of a given solutions, now we need to determine the specific conductance of that solutions. That needs to be determined. So before we determining the equivalent conductance, and see, we know that it's a knowing quantity, it's known quantity that we are going to prepare how much concentrations we need now to calculate the specific conductance. So specific conductance is equal to G into X. Okay, now what is X? X is actually cell constant. Now we need to determine the cell constant. So before we starting the experiment, we need to determine the cell constant, how far the two electrodes are separated, whether it is exactly 1 centimeter or 0.9, that actually matters. So in order to determine the cell constant, we have the formula, that is we will start with the resistance. Resistance is equal to L by A, where L by A is a cell constant. Okay, now just take a reciprocal, 1 by R, 1 by rho. So this is 1 by X. So 1 by R is conductance, 1 by rho is a specific conductance. Yeah, 1 by rho is a specific conductance. So this is just X. Now X is equal to specific conductance by G. Now specific conductance, in order to calculate X, as we stated earlier, we will take a known solutions, a specific conductance whose a solution whose specific conductance is already known, that is equivalent to, that is for 0.1 normal KCl as 2765. So we can substitute that, which is already known quantity, and the conductance can be measured. Now the G has to be measured, correct? The observed conductance, how to measure the observed conductance? Now this, once we measure the observed conductance of 0.1 normal KCl of the same solutions, then we can calculate X. This is X kg. So this is 2765, the observed conductance G. Now G has to be determined. Once G is determined, now X can be determined. Now how to measure this G? That is the questions. So in order to measure this G, what we will do is we will take the measurement of G, the conductance, by using a bridge that contains a resistance box. Now the solution whose conductance is to be measured has to be taken in the conductivity cell. The conductivity cell, we need to plot a diagram. So it's to be taken in the conductivity cell. So this is a solutions whose conductance is to be measured, a 50 ml of the solutions. Now we have this conductivity cell. Now this is a conductivity cell. Now the conductivity cell actually consists of an electrode which are made up of platinum, which are platinum coated. So which are platinum coated with finally divided platinum. So these are welded to platinum wires. This is platinum wires. This is platinum wires which are sealed through a two sealed glass tube. They're actually sealed through two glass tube. So here is actually two glass tube. Now this is the end will be closed. The tubes are firmly fixed in an these tubes are firmly fixed in an ebonite cover so that the distance between the electrode is not altered. So which is connected to a resistance box. This is a resistance box. Now this is completed with the circuit, that is with the conductivity cell. Now this is conductivity cell, conductivity cell. Now one end will be connected to a telephone. So here this end will be connected to a stretched wire, connected to a stretched wire. So from here, which is connected to a telephone, this is D. So this is AB stretched wire. So this is a telephone wire. Now this is a resistance box. The resistance box will have 1 ohm, 2 ohm, 8 ohm, 20 ohm, 100 up to 1000 ohm. So here the cell is connected to a resistance box. Here the cell is connected to a resistance box on one side and to a long thin wire AB on the other side, and the scale along a scale on the other side. Now some known resistance R is taken out of the resistance box. Some known, maybe 20 ohm, 50 ohm, whatever it may be, some known resistance R is taken out of the resistance box. An alternating current of about 1000 to 4000 cycle per second is passed through the solutions from AC. From the alternating current about 1000 to 4000 cycle per second is passed through the solutions. The sliding contact, so this is called as D. The sliding contact is moved on the wire. It has to be moved on the wire AB so that the minimum sound or no sound is heard in the headphone, in the telephone. That is the minimum sound or no sound heard in the headphone. If the sound is more, we need to remove more resistance from the box. We need to unload the resistance box frequently in order to minimize the sound in the telephone. So once the sound is minimum, we need to record how much the resistance is taken out from the box. That means we have recorded. So correct. Now we can go with the resistance of the solutions. So thus resistance is nothing but the resistance offered by the solutions that is taken in the conductivity cell divided by the resistance R. So that can be the length of BD divided by the length AD. Now if it is here, we'll get a minimum sound after taking some the known resistance. Now this distance AD, Now this distance AD we call it as the resistance R of the conductor, and this BD the resistance of the solutions. This BD we call it as resistance of the solutions. The length. Now thus knowing R, AD and BD, the resistance of the solutions can be calculated. Now by knowing the resistance R, the resistance R is taken from the box. It's maybe 100 ohm or 150 ohm or 250 ohm. So where we get a minimum sound that we have taken from the box. By knowing R, AD and BD, the resistance of the solutions can be calculated. The resistance of the solution is equal to the length BD, the length AD into R. So we get a resistance of the solutions, and we know that G is equal to 1 over resistance of the solutions. G is equal to 1 by resistance of the solutions. We call it as a conductance. So by knowing the conductance, we can substitute the cell constant X is equal to into G. So we have calculated G, we have determined G. Then after determining G, we can calculate what is cell constant. So after determining the cell constant, we can calculate the specific conductance. Specific conductance of the solution whose equivalent conductance has to be determined. Whose equivalent conductance has to be determined. So the equivalent conductance, so lambda EQ kappa into 1000 divided by C. Now the specific conductance of the solutions whose equivalent conductance has to be determined will be equal to G into X, where G is an observed conductance of the another solution. So this is a known solutions that we already calculated in R to X. X can be calculated from the known specific conductance. Once you calculated X, once you calculated cell constant, by knowing the cell constant we can calculate specific conductance by measuring the observed conductance in a similar fashions by using instrument. The conductivity, the solutions will be put into the into the conductivity cell. The solutions can be put into the conductivity cell, and by removing a known resistance, then we get a minimum sound or no sound in the scale. And rubbing this scale, that resistance can be known from the resistance, and by measuring length BD and length AD, we can calculate the resistance of the solutions in a similar fashion. That this observed conductance, this is already known. Observed conductance can be determined the above method simply. Then we can calculate the specific conductance. Once we calculate the specific conductance, we can put the specific conductance here. So by putting this specific conductance here, we can calculate lambda EQ, that is the equivalent conductance. Now once if we calculate the observed conductance, we can calculate the cell constant. So this is an observed conductance. After calculating the cell constant, we can take, so this is a known solution. So this the observed conductance of, so this is an observed conductance of a solution whose specific conductance is already known. By taking the known specific conductance of a known solutions, we can calculate the cell constant. After calculating the cell constant, now we need to apply Now we need to calculate the specific conductance. Now we need to calculate the specific conductance of a solution whose equivalent conductance has to be determined. Conductance has to be determined. So this can be done by measuring the observed conductance, specific conductance into G into X. This X already we have determined by using the specific conductance, which is already known quantity. Now the observed conductance can be measured by using the same method that we explained just now. So after calculating the specific conductance, we can get this. After determining the observed conductance, we will get the specific conductance by applying the specific conductance in the formula K into 1000 divided by C. We will get equivalent conductance. So this is a method to determine the equivalent conductance of an electrolyte.